Right, Mr. Palmer here. Before we start this video on hex, okay, make sure you go over your notes on binary and denary and you're fluent with column placeholders and that you can do the conversions quite smoothly, okay? Otherwise you're going to really struggle with hexadecimal notation. So the big questions for this video basically are, can you convert from denary to binary? From denary and binary to hex, and can you go from hex back to binary or hex to denary? And you need to understand why we use hexadecimal notation. So remember now, with base 16 notation, which is what hex is, we're basically storing 16 values, 16 possible values in a single column. Alright, so remember in our day-to-day we're using base 10, so we use it from 0 to 9, which is 10 numbers. Here we got 16, so we've got 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, okay, as normal. But then when we get to 10, we're going to represent 10 with A, because we want to use a single value in that column. So similarly, 11 is going to be B, 12 is a C, 13 is a D, 14 is E, and 15 is an F. Okay, so we've got these letters now representing single values. So what do I mean by that? Remember, we got columns, alright, placeholders, alright. So in our normal day-to-day denary that we use, remember it's a base 10 system, so our left-hand column is 10 to the power of 0, which gives us units, so we can store from 0, 1, 2, 3, 4, 5, 6, 7, 8, 9 in a single column. Alright, the middle, the next column to the left is going to be 10 to the power of 1, which gives us our tens, etc, etc. So the number 357 basically is 3 times 100 plus 5 times 10 plus 7 times 1, which gives us 300 plus 50 plus 7, which is 357. We're doing exactly the same thing in hexadecimal, but instead of using tens for the column placeholders, we're going to be using, or for the base value, we're using 16. So in a base 16 system, we've still got units on the right hand side. 16 to the power of 0 is 1, 16 to the 1 is 16. Alright, so instead of a tens column, we've got a 16s column. Then instead of a hundreds column, we've got a 256s column, because 16 squared. We're only going to be concerned with the right hand and the middle column, okay? Two columns only. So basically, if I got a number like 1A in hexadecimal, I want to convert that to denary, so our everyday number system. It's quite straightforward. Remember, the left hand column is equivalent to the tens column, so in essence it's a 16s column. So I'm going to do 1 times 16 to work out that value. I'm going to add to that whatever the right hand column is, because that's just the units. A is 10, and so my number basically is 16 plus 10, which is 26. Alright, now I want you to try this one out. I'm going to hit pause, or you should hit pause. And now if you come back, 2E basically is, my 16's column is going to be 2 times 16 plus whatever E is, and that gives me 46. If at first you don't succeed, dust yourself off and try again. Hit pause, have another go. And so you should have got 4B, alright, 4 16s plus B, which is 11, gives you 75 overall. Now, how did you go in the other direction? How do we convert from our normal everyday denary to hexadecimal? It's the opposite, okay? In this case, now we want to work out how many 16s fit into the number. So instead of multiplying, we're going to divide. So if I want to convert 25 to hexadecimal, basically 25 divided by 16 is 1. I have a remainder of 9. So therefore my left hand digit, okay, is going to be 1, and my right hand digit is 9. You can confirm that by doing the by converting it back in the other direction. You'll see 1 times 16 plus 9 gives you 25. So you try it out now, okay? Hit pause. If I were you, I would do the conversion back in the other direction to actually confirm that you've got the right answer, to check. Alright, so if you hit pause and you try it again, you should have got 46 divided by 16 is 2, remainder 14. 14 is the same as E, and therefore your answer should be 2E in base 16. Alright, if you want to have one more go before we move on. So 73, similarly 73 divided by 16 is 4, remainder 9, and that means that your number is going to be 49 in base 16. So second big question though was, why do we use hexadecimal notation? Alright, now it's all to do with the range of values you can store in a nibble. if you think back to that, you've got a nibble, you had 4 bits, okay, so you've got column headings of 1, 2, 4, 8, and you add them together. Basically you can store a range of values from 0 to 15. Very important, because actually that corresponds to a single hex digit, which goes from 0 to F, where F is equal to 15. So in essence what we're saying is that we can store or we can write a byte, note a byte by hand using 2 hex digits, alright, 10 and 3. So sorry, what am I saying? The left hand, I've got one whole byte there, 8 bits. I'm going to break them into 2 nibbles. So what I need to do now is go look at those 2 individual values for the nibbles. So 1010, I've got an 8 and a 2, add them together, I've got 10 on the left hand side, and 0011 is a 2 plus 1, which is 3. 10 is the same as A, so that actual byte can be written down using A3. Alright? Another example to try and, or an actual real life example so you have an idea, is that HTML has got 16.7 million possible colors if you use an RGB, alright, red, green and blue. Would you rather read that long binary string for the red, the green and the blue, or that really short simple hex code at the bottom, okay, when you're coding? Obviously you want the bottom color code, because it's going to be easier for you to work with and understand. Alright, so the reason for using hex is not because computers can understand hex. I don't know what's wrong with you students and why, like, so many of you seem to think that that's the reason. Okay, computers don't understand hex, computers only understand binary, but humans understand hex easily. So we can use a single hex digit to represent a nibble, therefore a byte can be shown using 2 simple hex digits, and the knock-on impact of that is it's easy for humans to read, and humans are less likely to make mistakes when working with large numbers, okay, which they would do if it was all just 10101100001111, whatever it is in binary. Alright, so now you have a go at basically trying to convert these numbers. Alright, so remember we got a byte, you're going to split that byte in 2, you're going to convert the left digit, sorry, the left nibble to get 1 digit, you convert the right nibble to get the other digit, and then you join them together to get the binary in hex. I'm going to hit pause, you have a go, and you should have got left digit is 8 plus 2, which is 10, and the A, and the right digit is 3, and you get A3. Okay, how did you go in the other direction? Well, technically if you were smart enough you would have hit pause by now already and had a go at it, because it's really easy. Exactly the same thing. Split the number in half. Alright, that was a bit rude, isn't it, me saying if you're smart. What I should have said is if you're getting it, but here we go. 3 is the same as 0011. On the right hand side, F is 15, which is 1111, and therefore the total number in binary is going to be 0011, and then etc, etc. Right, you have a go by yourself. B9, hit pause, and you should have got, split the number in half. B is the same as 11, which is that. 9 is an 8 and a 1, and therefore join the 2 bits together to get the complete byte in binary. Okay, and that basically is showing you how to convert from denary to hex and binary to hex and back in the other direction. And you should understand why we use hex, because 1 hex digit can store the same range of values as a nibble. Therefore we can make it easy for humans to understand long binary numbers by using 2 hex digits to represent a single byte. Alright, thank you very much.